a great pleasure to introduce Yue Yu from Caltech, who is going to tell us some story about non-Archimedean quantitative theory from the variance.
Thank you very much, Ludmil, for the introduction, and thank you so much for the invitation. It's my great pleasure to be here, especially since these 2 years of COVID. I'm really happy to meet many colleagues and friends here again in Miami. The title of my talk is Non-Archimedean Quantum K-Theory and Gromov-Witten Invariants. It's based on my previous joint work and also ongoing joint work with M Porta. Here is the plan of my talk. I begin with motivations from mirror symmetry, and then I'll give a review of derived non-Archimedean geometry and the representability theorem. After that, I will talk about the modular stack of non-Archimedean stable maps and the Gromov compactness theorem. And then I will discuss the numerical enumerative invariant, because eventually we want to get numbers. And finally, I will mention the geometric relation between the derived modular stacks, and from which we will deduce all the expected properties for the numerical enumerative invariants. So let me start with motivations from mirror symmetry. Let's recall that a smooth projective variety X over C is called Calabi-Yau if its canonical bundle is trivial. In other words, if it has a nowhere vanishing holomorphic volume form. So examples include elliptic curves, abelian varieties, K3 surfaces, or any hypersurface of degree d+1 in d-dimensional complex projective space, and of course, lots of others. Mirror symmetry is a conjectural duality between Calabi-Yau varieties. So roughly, mirror symmetry says that for any Calabi-Yau variety X, we have some mirror variety X check such that a list of deep geometric relations hold between X and X check, involving Hodge structures, Gromov-Witten invariants, Fukaya categories, derived category of coherent sheaves, SYZ torus fibrations, etc. A more careful study of mirror symmetry shows that mirror symmetry is not really a duality between individual Calabi-Yau varieties, but rather a duality between so-called maximally degenerating families of Calabi-Yau varieties. So example of maximal degenerating family is type 3 degeneration of K3 surfaces. Here is a picture. We have a K3, smooth K3 surface degenerates to this soccer ball, like it's a singular SNC degeneration, singular fiber. So each piece is like a smooth surface. Okay. Yeah. So in general, when we have an algebraic family of varieties over a punctured disk parametrized by T, we obtain a single variety over C double parenthesis T, the field of formal Laurent series. Because when we have a family over punctured disk, it's given by equations with coefficients depending on T. Therefore, it's just a variety over this field. And this is in particular, this is a non-Archimedean field because it has a norm. The norm of X is given by exponential of minus valuation with respect to T. And it's called a non-Archimedean because this norm satisfies this strong triangular inequality. So norm of X plus Y is less than or equal to the maximum of the norm of x and the norm of y. In the Archimedean field, it will be norm of x plus norm of y. Here it's maximum, so it's called the non-Archimedean. And and the non-Archimedean geometry is an analog of complex geometry over such non-Archimedean field. So for example, this field. And using non-Archimedean geometry, we obtain a more general and a more symmetric formulation of mirror symmetry as a duality of non-Archimedean Calabi-Yau manifolds. So we can add the condition about degenerations and so on. So it has the following advantages. First of all, I already said it's a more symmetric version of mirror symmetry, because usually we may think mirror symmetry like one side is some variety, like symplectic manifold is one symplectic manifold, and the other side we consider some family of complex manifold. With this non-Archimedean language, we can have both sides just the non-Archimedean space. So it's more symmetric in this sense. And also it's more general, because the non-Archimedean thing is essentially some kind of formal deformation. So we can work formally without worrying about complex analytic convergence. Of course, we can always ask about complex analytic convergence later, but just this non-Archimedean version first, using this non-Archimedean version first, we can just forget about the complicated questions about complex analytic convergence. We work formally, and later we can consider this complex analytic convergence. The second advantage is that for the XYZ torus vibration, the analog in non-Archimedean geometry, its existence is proved and also can be explicitly constructed. For example, it's shown in my work with Johannes and Chen Yang. And finally, in this non-Archimedean picture, we also have new ways to count curves with boundaries, and they give rise to wall crossing formulas. So all these considerations motivate an analog of Gromov-Witten theory in non-Archimedean geometry, because now we are saying this non-Archimedean picture is more symmetric, it's kind of easier, also has XYZ vibration, so we really want to count curves inside. And we know in usual symplectic or algebraic geometry, the curve counting theory, which works in full generality, is the Gromov-Witten theory. We have many other nice theories like DT theory, stable pairs. They work usually under some other, like only for 3 Calabi-Yau or some other condition. Gromov-Witten is the most general. So we want to have also Gromov-Witten in the non-Archimedean setting, and that's the motivation. Yeah. So in order to do this, let's just recall how do we do Gromov-Witten in the classical setting. In symplectic geometry, I think now there are several theories. And in algebraic geometry, the approach is via perfect obstruction theory developed by Baron Fantecchi and Li and Tian. So we first tried to carry this theory over to non-Archimedean geometry, but it doesn't work so well. It doesn't really carry over. So our approach in the non-Archimedean setting is the following. We develop a theory of derived non-Archimedean geometry. And using this derived theory, we deduce non-Archimedean, this quantum K invariants, or this K theoretical version of Gromov-Witten invariants. And we also deduce non-Archimedean Gromov-Witten invariants. So we use a different approach from the classical setting, which is more adapted to the non-Archimedean world.
I thought derived geometry is basically the same thing as perfect obstruction. What was the difference?
Perfect obstruction theory is something you can deduce from a derived structure. It's not equivalent to a derived structure. That's the first thing. And the second is that, okay, so then, for example, when you have natural relations between the derived structure, if you want to express in terms of perfect obstruction theory, usually you need to make some extra choices. It's like something you get after the derived structure. That's one thing. And another thing is that invariant Fantecchi is not just a perfect obstruction theory. So you go from perfect obstruction theory to Gromov-Witten classes, one has to use this intrinsic normal cone construction. So there are more things going on in this construction which do not readily translate, cannot be easily translated into an analytic setting. Thank you for the question. Okay. Are there any other questions? Okay. Yeah, so then now I said we use this some derived version, derived geometry in the non-Archimedean setting. Let me give a quick review of what is derived non-Archimedean geometry. Yeah, so, okay, so what is the derived non-Archimedean analytic space? Let's first recall the definition of a derived scheme. A derived scheme is a pair X or X consisting of a topological space X and a sheaf of simplicial commutative rings on X, satisfying the following conditions. Yeah, so usually a scheme, like a classical scheme, is just it's a locally ringed space, meaning that we have a topological space together with a sheaf of rings. To make it derived, we replace the sheaf of rings by a sheaf of some simplicial rings. So this is how to make things derived. You can also, if you like DG rings, or they are you lead to some kind of similar series. Simplicial rings is the best. And we ask two very basic conditions. First, when we take pi0 of our ring, we want to get a usual scheme, a classical scheme. And when we take higher pi I, we want to get quasi-coherent sheaves over pi0. So that's a very simple definition of what a derived scheme is. You may, if you didn't study derived geometry before, you may think, oh, the definition is so simple. Why is derived geometry like so complicated, uses so much complicated machinery? It's because although the definition of derived scheme is simple, but to put them into a category, in other words, to consider morphisms between them, that kind of requires more work. But the notion of derived scheme is actually simple. Okay, so now we want to adapt the above definition to non-Archimedean analytic geometry. In other words, we want to find a way to impose additional analytic structures on this structure sheaf OX. Because what we want to do some analytic geometry. And just now we only have the algebraic structure. We want to impose analytic structures. So for example, we want to have a notion of norms on the sections of the structure sheaf. And also we would like to be able to compose sections of the structure sheaf with convergent power series. Yeah, we want to impose analytic structures. So our first attempt is to enhance simplicial commutative rings with non-Archimedean analytic structures. So what is non-Archimedean analytic structure? in non-Archimedean geometry, the building blocks are so-called affinoid algebra. They are special types of Banach algebras. And now, if we kind of want simplicial commutative rings with non-Archimedean structures, we want some kind of simplicial commutative affinoid algebra or simplicial commutative Banach algebra. This turned out to be very difficult because this Banach structure and the simplicial structure, they do not mix very well. So one can get many pathological examples. There are works in this direction, but we kind of couldn't move forward.
What is the fundamental problem in trying to do that?
It's because in general, Banach algebras, they are very difficult to work with. You cannot, like you don't have a notarian. They are not a notarian. You know, to set up a geometry, you need very basic properties. You want them to be notarian. You want ideals to be closed, for example. And also, if you have a morphism between two Banach algebras, and if it's a morphism of algebras, then you may worry whether it's also a continuous morphism. Like all these kind of, you don't want to mix this algebra with continuity or these complicated things. So it's kind of a very non-trivial fact that in non-Archimedean geometry, if we work with affinoid algebras, all complicated analytic issues, they kind of disappear. But they don't disappear with Banach algebras. And if one wants to consider simplicial things, then we will also be taking resolutions, things like that. And we very soon get into things of not of finite type.
I mean, in the Archimedean world, there is a good theory of Banach analytics spaces and Banach analytics stuff and so on. I mean, but you have to tweak the Banach structure, but there's no. I mean, I don't know any of this. So is there any, is that the work that you are saying?
I think they are somehow going into this direction by some dagger algebra or some other algebra, but that really amounts to rewrite all the foundations of analytic geometry, which is too kind of far from what we want to do. So our strategy is to use the theory of pre-geometry and the structured topos of Jacob Lurie. And it's actually really an ingenious idea of Lurie that somehow to get a derived theory, we kind of don't really need to care what's inside this classical theory. We can just build a machine and we input into the machine some classical theory. And then as a black box, the machine will just output for us some derived theory. So we don't need to go back to the classical theory again, like to work out all the complicated lemmas or properties of algebras. We can just take the classical theory, put it into this machine called the pre-geometry and the structured topos. Then we will just obtain this derived theory.
How does this avoid this problem you just mentioned, that when you have to take resolution, you go from finite to infinite?
Because you want to take a resolution as in like resolution for algebras, not for modules. For modules, you can take, for algebras, you will get infinite as modules, right? You take a resolution, like projective resolution, for maps of algebras, then what you get, although it's finitely generated as algebra, but not as modules. Also, it will not be even finitely generated as algebras. So in non-Archimedean geometry, it's like in algebraic geometry, you cannot always work with things, varieties of finite. Like to do resolutions, we will get things not of finite type.
When you input whatever theory into the Lurie business, you input a theory including things not of finite type or only a theory of finite type?
I will show you. We will input things just geometrical objects. Not at all. You don't need to care anything about the underlying algebraic framework. Yeah, so the theory also works for complex analytic geometry, and it will also produce for us a complex derived complex geometry. And that's Lurie's original motivation for setting up this machine. Yeah. So the idea is to use the language of infinity category and infinity topos to generate derived sheaves starting from simple classical objects. And thus we can bypass any model dependent construction. So either simplicial algebras, EG algebras, we don't need to know anything about them, because these are the things that cause us trouble in the analytical world. So we can bypass all these like models and directly get a conceptual understanding of the derived space. Yeah, so I will go now. Let me go pretty quickly through this formal machine, because it's quite it's a categorical formal theory, probably not easy to understand at the first when you first see it. So I'll just say that a pre-geometry is a category equipped with a class of admissible morphisms and a Grothendieck topology, satisfying some compatibility conditions. So for example, given a non-Archimedean field, we can consider this pre-geometry T et al. Consists of smooth varieties as objects, et al. Maps as admissible morphisms, and et al. Topology as Grothendieck topology. And they said the compatibility relation. Yeah, so if we input into this machine, this pre-geometry, we will get the derived algebraic geometry for varieties over K.
Am I allowed to input into this machine open subsets of Euclidean space? Inclusions of open subsets of Euclidean space?
I think for differential geometry, there is something tricky. Maybe I would.
But it seems to satisfy your definition.
What kind of morphism?
Inclusion of open subset.
Inclusion of open subsets. Yeah, I guess it will produce something, but probably not the. I'm not sure. I will think about it later. Yeah, for example, here in the algebraic case, we want to put et al. Maps. You can also put the Zariski as well. Anyway, so here, these are the two examples that we consider. Okay, so the analytic version of this pre-geometry, instead of varieties, I take analytic spaces, smooth analytic spaces, et al. Maps, and et al. Topology.
But the word smooth and means as usual finite dimensional.
Yeah, just these are classical objects already considered for more than 50 years.
But they in particular finite dimensional.
In non-Archimedean geometry, people only study finite dimensional spaces. Thank you for the question. Okay. Yeah. So now we have the free geometry. How do we get to the derived space? The derived space. So there's second formal definition. If we have free geometry T, then and I fix X infinity topos. If you don't know what it is, you can just think of as an example the category of sheaves of spaces on a given topological space. That's infinity topos. So you can think of X as an infinity version of topological space, and the T as some kind of rings. So now we want to define this notion of ringed space, and that's called or a sheaf of rings. Sheaf of rings. Yeah, so that's called a T structure. Yeah, then it's again just a formal definition. It's a functor satisfying some compatibility conditions. And the geometric idea is that it is like a fancy way of saying what a sheaf of rings is, because now we want a sheaf not just probably of rings, but also rings with extra structures. And here is the idea. Okay, so here is the idea behind this abstract definition. We think of this T on K structure O as a sheaf of derived rings equipped with an analytic structure. Yeah, so maybe I should just here we have compatibility condition 1, 2, 3, preserving finite products, like sends some pullbacks to pullbacks, sends coverings to coverings. Yeah, so let's see why these conditions gives a sheaf of rings with extra structure. Okay, so first I just take, yeah, maybe I should show this. So it's a functor O from the pre-geometry to the topos. And now I can just evaluate O on the affine line A1. A1 is smooth, so it's an element in our category T. So I can evaluate O on A1 and denote it by F. So it's an element of this infinity topos, which we can just think of it as some sheaf on the topological space. So we already get a sheaf. Now we have the sum operation from A1 times A1 to A1. And since the functor is product preserving, we obtain a sum operation on the sheaf. And similarly, we also obtain a multiplication on the sheaf. So therefore, we have a sheaf with plus and a multiplication. So we can intuitively think of F as a sheaf of simplicial commutative rings. It's really nice. We don't need to talk about model structure or to define what is simplicial commutative ring. Just by doing this, we get like a model independent version of plus and times. They are automatically derived. And the second, we also have we have some norm, because if I take the closed unit disk in A1, and since by definition our functor O sends pullback of admissible morphisms to pullbacks, and this inclusion induces also an inclusion at the level of sheaves. So O of D1 will be like a subsheaf of this F. And therefore, we can think of this subsheaf as the subsheaf of F consisting of functions of norm less than or equal to 1. So in this functorial way, now we somehow get a norm. And finally, for any convergent power series, just by functoriality, we also get a morphism for this, which we can think of it as a composition with any convergent power series. So you see this, it's a really nice idea that using very simple categorical language, now we kind of get with minimal effort all the derived structures that we need or on the analytic spaces. In other words, or equivalently, we get all the analytic structures that we need for the derived space.
So for your main example of these analytic things, how should we think of this O of A1? Is this more explicit?
O of A1 is just like our structure sheaf.
But what is it?
If you take pi 0, it will be a usual analytic space. And if you take pi I, they are the correction terms. It's exactly what we want.
But you're saying it's model independent. But you are feeding something into your machinery. So it's not a simplicial heap of rings, or is it?
It's no, it's not a simplicial because it has all the extra analytic structures.
He hasn't yet told me how to use a single example. Well, that was, I guess that was my question. So you haven't produced it, or you have?
The example will be the stack of stable maps.
Okay.
That will be one. Of course, we can have trivial examples.
Well, I want to ask about trivial. Is there some of your native theorems that you're saying that?
Of course, the embedding is fully faithful. Yeah, it's something requires a proof with Marlow. That's like we wrote it in our first paper when we started studying this. We proved it has fully faithful. So all this, for this series, one has to spend some effort just to check the basics. We checked the basics. Okay, so now we are ready to give definition of derived non-Archimedean space. It's now, once we figured out a way to put the analytic structure onto derived structure, we can just mimic the same definition as for derived scheme. So a derived K analytic space is just a pair XOX consisting of infinity tuples X and some technical condition, and this P on K structure OX. So we really think of this as some kind of topological space, underlying topological space. Although we already know that in non-Archimedean geometry, we do not really have underlying topological space. So we do not really have simple underlying topological space. Either we have to go to Berkovich space or like Huber's edit space. And yeah, anyway, here we just work with topos. And then this OX, you just think of as structure shift, as I already explained. Then the condition is exactly parallel to algebraic geometry. So we ask that when we take pi 0, we get the usual analytic space, and when we take higher pi j, we get the coherent shift over pi 0.
What is the difference between OX and OX?
Ouch just means I ignore the analytic structure. Yeah.
And what is
Good
pi
question.
0 here and pi j? This is some functor, right?
Here, we can take, because
This is,
in particular, these are shifts of what you can think of as topological spaces. So we have the homotopy groups. Yeah. Okay. Yeah. So then, as Vivek was asking, what is an example? So we have, of course, all the non-derived things. They are examples, and there are other easy examples. For example, we prove the existence of fiber products. Then one can construct non-trivial examples. But in practice, the derived analytic space, in order to construct them in practice, we use the representability theorem. Yeah. So we prove the representability theorem, which essentially says that any reasonable analytic moduli functor should be represented by some derived analytic space. And the precise statement is that if some analytic moduli functor has the structure of derived analytic space, I should say the following are equivalent. So it has the structure of derived analytic space, and the second is that it satisfies all the expected properties of a reasonable moduli function. So for example, compatible with Post-Nikov towers, meaning that this things like Schlesinger criterion, things like this, and having some cotangent complex. So cotangent complex, it controls the deformation of the structure series, and also the truncation is good. Okay. So let me remark, maybe this is Yeah, let me just remark that this representability theorem has two implications. First, it's a philosophical implication. So this is the word. Yeah. So first, philosophically, it says that our notion of derived analytic space is natural and sufficiently general. So in other words, any reasonable analytic moduli functor has the structure of a derived analytic space. Because when we define, we can define a derived analytic space in whatever way we like, then we may worry whether our definition is kind of useful in practice. And this is exactly confirmed by the representability theorem, saying that our definition is kind of already good enough that it contains all the, it represents all the modular problems, any reasonable modular problems. And the second implication is practical implication, because these conditions are very easy to verify in practice. So the theorem gives plenty of down-to-earth examples of derived analytic spaces.
Is the proof roughly analogous to Lurie's proof?
We mainly kind of try to make the parallel thing. It's easier than Lurie's theory. What we do here, it's in some part easier, in some part a little bit more complicated. The complication is about with this analytic structure. The simplification is that we already assume that the truncation is representable. And in the algebraic world, one doesn't need to assume this, but one then has to use this Popescu smoothing theorem. And I hope this Popescu theorem can also be worked out in analytic geometry, but I don't know. I don't think people have worked on this. One can, yeah. So there is still improvement one can do in this analytic version. Yeah. Okay. So we also have the similar thing for stacks. Okay. Now, yeah. Now my goal is to always. We have very concrete goals to produce the curve counts for the purpose of mirror symmetry. So now we study stable non-Archimedean stable maps, the modular stack of non-Archimedean stable maps. Yeah. So stable map in the non-Archimedean setting is defined exactly as in the algebraic setting. We have some base P, we have family, nodal family of nodal curve and sections. Stable means it has a finite automorphism group. Okay, so then as an application of the representability theorem, we obtain the associated derived modular space. So we obtain a derived enhancement of the modular space of non-Archimedean analytic stable maps. Here is the precise statement. So we show that the derived modular stack of point n point the genus G stable maps into X is representable by a derived K analytic stack, non-Archimedean analytic stack, which is locally finite representation and derived LCI. So here LCI means that the cotangent complex is perfect and in tau amplitude 1 minus infinity. So it's what's usually called quasi-smooth in the derived setting, but in non-Archimedean world, we have already quasi-smooth already means something else.
I thought the whole point was to get the omega of the derived structure, and that is a cotangent complex, but now you want to use, how do you define the cotangent complex without first entering the derived structure? What is it for you?
cotangent complex, it's defined like as something which represents these derivations, like in the, so as a canonical definition. Yes.
I thought LCI was supposed to be cotangent complexes of 2 degrees.
Yeah, but if you consider stacks, it will have this stacked degrees. Otherwise, it's 2 degrees. Yes.
This theorem, after you know representability theorem, it's like local calculation.
One has to verify the properties of.
No, sorry, I just meant about this derived LCI. That's just local calculation on functor, or
That's just the calculation of the cotangent complex. Yeah. Okay. Yeah. So in order to get the numbers, we also need some compactness, because to get any numbers, we need both compactness and the transversality. So for compactness, the Gromov compactness, I studied it a while ago, and I talked about it also in the Miami conference here. So I don't talk about it this time. Yeah, okay. So as I said, our ultimate goal is to produce numbers for mirror symmetry. Now the question is, how do we get numbers? In other words, numerical enumerative invariants from the derived structure. There are 2 ways to get numbers classically from this derived structure. One is using K-theory, and from which we get so-called quantum K invariants. They are developed by Giventhal and Lee. Yeah, so actually it's written after Barron and Fantacchi, but it's easier than Barron and Fantacchi to get this K invariant. So the second way is by intersection theory. Then it's by Barron and Fantacchi we get Gromov-Witten invariants. Yeah. So the K-theory version works similarly in non-Archimedean geometry, because we can still do vector bundles, things like that. And then it's quite easy to do the parallel construction. In the non-Archimedean world, we have this evaluation, we have the derived space, derived modular space, evaluation maps, stabilization maps, then the K invariants, we just pull back by evaluation map, push forward by stabilization. So the advantage of derived is just that we don't need to further tensor with the derived structure sheet, because everything is already derived. Yeah, so that's for the case theoretical invariance. However, intersection theory, if we want to get the actual, this genuine Gromov-Witten invariant, then we need to do some intersection theory. But the intersection theory just cannot work in non-Archimedean geometry, nor in complex analytic geometry. They just don't work in analytic geometry. So by intersection theory, I mean, for example, what's written in Fulton's book. The reason is that we just cannot intersect the cycles. In algebraic geometry, we have moving lemma to move cycles into transverse positions and intersect, but in analytic geometry, there are not many cycles to move around. Or in Fulton's construction, we use some chain classes, and in analytic geometry, we cannot, when we have vector bundles, we cannot take chain classes to get a cycle. We can only get something weaker. Some chain class is some differential forms, things like this, but not algebraic analytic cycles. So we only have weaker things. Yeah. The solution is that because we only want to get some numbers, so probably we don't need such refined intersection theory. All we need is just some cohomology theory. Because from cohomology theory, I mean, numbers are eventually just some degrees. So as long as we can talk about the degrees, that should be good enough. So once we kind of agree to work with cohomology series, then in non-Archimedean geometry, we just have so many choices of cohomology series. People are really devoted really lots of effort to set up all different kinds of cohomology series in non-Archimedean geometry.
Can I ask a question?
Yeah.
You could imagine a different solution where you just it's supposed to be a map from K-theory of cohomology. Ignore the fact you don't know what cohomology is, just formally declare that that map should work.
Yeah, that's a great question. Actually, this is what we initially tried to do. But that map will require some Riemann rock.
Yeah.
And that we still don't know how to prove.
But never mind proving it, just declare that it's formally true and then use that to.
But then you cannot prove the properties.
I see.
You can define the numbers. In order to prove any property, you will need some Riemann rock formula. And it's just, actually we spent a long time and still we don't know how to do this Riemann rock. Because doing Riemann rock, in algebraic geometry, we have this gross and exclude. In complex geometry, one goes through some analysis. In non-Archimedean geometry, also with this, it's not clear. Yeah. So once we agree to work with cohomology theory, we just have so many choices, and we have, and they are all kind of different. So we have a data cohomology. We can work with a data cohomology. Then the drawback is that a data cohomology is very well developed. The drawback is that the invariants we will get, they will live in QL. So, but it's a little bit disappointing because we want to count the curves. We want some number of curves. We don't want an analytic number of curves. And then it raises further the question about independence of L. And besides a data cohomology, we have the RAM cohomology. Then similarly, we have this trouble. The RAM cohomology, we get invariant in K in the ground field. So still not so good. It's like power series, not clear what other coefficients mean. So then there is this very recent theory by Berkowitz called the integral A-Data cohomology. And using that, we will be getting invariants in Q. However, this theory is very recent, and the functorial properties, they are not yet sufficiently developed to be used in enumerative geometry, and also it has a restriction of the ground field. Of course, from our motivation, somehow we can content ourselves with this ground field, but it's just nicer if things kind of are independent of the ground field. Yeah, so then very luckily, now we have a much more powerful theory that we can work with. It's the theory of rigid analytic motivic cohomology by Ayub. And this gives rise to invariance in Q. And it also works over general non-Archimedean field. So it's kind of natural that when we have trouble with the analytic cohomology, we go to motives. Yeah, so actually, I was asking Joseph Ayub about some functorial properties when he developed this theory, and I was asking whether one can have these properties useful for these Gromov-Witten invariants, and then Joseph with his students together recently, also motivated by these questions, they developed this 6-functor formalism. So now the theory is very nice and pretty complete. Roughly, for any analytic space, we have this infinity category of étale k-analytic motives with rational coefficients. And furthermore, so it's denoted by this notation. This étale and the Q, they simplify the story. One can put Misnevich and also the coefficients or other coefficients that makes things more complicated. So with this simplification, étale and the Q, we have 6 functors. We have 6 functors. And you know that once we have 6 functors, we have all the cohomology series. Yeah, so then we can define motivic cohomology and the motivic Borel homology.
This infinity category, is it stable or something, or just some?
Yeah, they are stable categories. Yeah. So also, so this theory is really, I think it's really satisfactory in the sense that, you know, in algebraic geometry, these motivic cohomologies, they give rise to Cho groups and higher Cho groups. And that's exactly like the intersection theories are about. And here in the non-Archimedean world, although we don't know how to construct any Cho groups, but we have this motivic construction. And they are supposed to kind of provide us some intersection theory that we kind of, we are unable to construct by hand in the analytic setting. And it's very mysterious. Why, like, what are these groups actually? But for our purpose, they are sufficient since we don't really need to know these groups. All we need to know is like, what is the group, like when X is a point, and also some functorial duality. That's enough for us to get these invariants. Yeah, so once we have this cohomology series, this very nice cohomology series, we do the deformation to the normal cone, the derived analog of deformation to the normal cone following Kang. So in paper by Kang and Dean, Reed, they developed this derived theory of deformation to the normal bundle. Here, in the derived world, it's nicer, not a cone, it's actually bundle. And then we can construct this virtual fundamental class by considering virtual fundamental class by considering this upper Schrick map, which is by definition, first we have something here, we pull back to the total space of deformation to the normal bundle, and then its normal bundle, we have homotopy equivalence, so it goes back to X. Yeah, then this virtual fundamental class, it's just the upper Schrick of 1. And also this theory is just so general that first of all, it's relative. Second, we don't even need to assume compactness of anything. It just works for any, like, because usually when we talk about a virtual class, we want already some kind of compactness of modular space. Here we have virtual class living directly in Borel homology. So the virtual class issue is totally separate. Is now totally separated from the compactness issue. Okay, so once we have the virtual class, then the Gromov-Witten invariants can be defined in the usual way. Pull back, cap with virtual class and push forward. Okay, so yeah, so in this, yeah, so finally, using this powerful machinery in derived geometry and also analytic geometry, we managed to get these numbers. Then, of course, we have the question that whether these numbers satisfy the expected properties of Gromov-Witten invariant. You know that either in algebraic geometry or in symplectic geometry, it's kind of quicker to define Gromov-Witten invariants than proving all the properties of Gromov-Witten invariants. But usually people just don't prove the properties. But here, once we use the derived language, it actually feels much, also it's kind of more comfortable to show the properties, because now the properties they will just follow from very natural geometric relations at the level of moduli stacks. We don't, since the way to go from moduli stack to numbers, it's just some kind of now it's kind of some kind of conceptual, some functorial way, and we can just think of it as a black box. We don't really need to care too much about this. All we need to do is just to prove some geometric relations at the level of the derived moduli stacks. And these geometric relations are very natural to guess and to formulate. Yeah. So we establish the expected properties of these numbers just by proving some natural geometric relations at the level of moduli spaces. So these relations are stated in terms of a little bit finer data. One has to consider some degenerations at the domains and so on, a little bit finer, like these invariants associated to trees. And then, so then the theorem is that these finer moduli stacks, so for invariants associated to some trees called tau beta marked stable maps, they satisfy natural geometric relations with respect to elementary operations on these graphs. Yeah, I should say graphs instead of trees, because I have been thinking too much about the rational Gromov-Witten. Here it's for any genus. Yeah, and then these relations, they are exactly the same relations you would write for non-derived moduli space, but now you just put the derived everywhere, and that is the relation. So it's completely something you can guess. Like for products, if we have disjoint, we take disjoint union, we get the product. If we cut an edge, we get the pullback, derived pullback diagram. So here, if you remove the derived structure, it's something obvious, because when we cut an edge like this, or we cut an edge, then this moduli space is exactly like the subset of that moduli space where 2 points I and j, they go to the same place. And here, the derived version, you just put the derived, it still holds. And we also have this universal curve about forgetting tail, and also some other property for forgetting tail, and some property for contracting edges. Yeah, so they all work. And these relations are exactly what you expect. But let me just finally, before I stop, let me just remark that although the relations are exactly what you expect, but once we put the derived structure, it actually, it contains a lot of like powerful information. So just the very simple case for the universal curve relation, in the case where tau is a point, then the relation that I showed in the previous page says that the forgettable map from mgn plus 1 to mgn is equivalent to the universal curve. And this is something which we know. It's like in the classical case, and now we proved that the same thing holds with derived structure. And this intuitive statement, in fact, incorporates all the information about virtual counts with respect to forgetting a tail. And classically, one has to do something extra to get it. Yeah, so yeah, let me just stop here. Finally, one can also consider higher multiplicities, relative invariance, and so on. And I will stop here. Thank you very much for your attention.
Questions?
Yes,
In terms of explicit computations, I mean, it looks totally uncomputable, but you should have some easy cases that you can actually feed into the computations to be able to do computations.
Yeah, so first of all, if things are coming from algebraic geometry, we actually have comparison theorem that will fit with algebraic geometry case. And when things are totally non-Archimedean, then I hope that we will eventually be able to compare with the invariants that you have been working with Mark. And actually, I was discussing with Mark like 2 weeks ago that I hope these non-Archimedean invariants are just equal to the log invariants, because for non-Archimedean, any non-Archimedean space, we have a formal model. And then on the special fiber, we have induced log structure. And I think this non-Archimedean invariance must be equal to the log invariance that you define for the special fiber.
Sure, if you have a formal family, yeah. But I mean, do you have an unobstructedness result? Like, is there some kind, I mean, it's all derived, but is there some case where you say it's classically unobstructed? Like, I don't know what you call this, the pi zero part of some derived thing is unobstructed, and then hence the
oh, you mean
kind of
like smoothness?
Yeah.
Yeah, yeah. So we smoothness, one can prove it for any kind of LCI. Yeah, any LCI, this derived space. For example, if it has expected dimension, then it is just smooth. It's something we had a section about this. So it's kind of a general property about LCI space.
Other question? Yes.
I have a question about this reason.
This,
So the Riemann-Roch theorem.
yes.
I think that there's some like modern proofs of this Riemann-Roch theorem, relatively recent, which is categorically Riemann-Roch. There's factored into 2 steps. One step is pure nonsense, and then one step is HKR theorem. Do you know what I'm talking about? This like toe in someone, and there's one by Stronsky.
That's for the.
In particular, they give the Riemann-Roch theorem.
But that's a weaker version, because if you use HKR, it's for this, then the Riemann-Roch only goes into this Hodge cohomology.
Yeah, sure, but I mean, maybe not this motivic level of there. But I just wanted to ask, does that argument work in the analytic setting, or does it not work in the analytic?
Yeah. So first of all, whether we can consider this Hodge cohomology, this like HQ of omega p.
Yeah.
These things, of course, it makes sense also in the non-Archimedean world, but but they don't give the numbers that we want, right? Because I mean, if we have assumed Hodge decomposition, then they will give what we want. But if we don't assume Hodge decomposition, then probably because we want some degree eventually. So I don't know if, so that's one thing. And another thing, it's of course an interesting question, separate to Gromov-Witten invariants, just whether we can do this proof you mentioned, this HKR version in the non-Archimedean setting. I think with model and Marco, we were discussing it a while ago, and for the HKR, and then the model, I think maybe they have some paper about HKR, not in this setting. Yeah, I don't remember what didn't work in the. I think so I don't know which proof of HKR you have in mind. We were looking into some book of Kashiwara and Sharpihai, and there the proof is analytic. It's working with differential forms. So this one, it doesn't, we cannot make it work. Then there's maybe some algebraic proof. We thought about this, but then we didn't pursue this direction since we got into all this complication about HKR, Riemann rock. They are just much more complicated than what I explained here. So, but now we go directly into this like this motivic cohomology. It kind of bypasses all these complicated questions of HKR and the Riemann rock.
Other question? Well, let's thank Tony again.
Thank you.